The next set of hydrological analyses you need to do are to design for the high flow scenario. So this would be the scenario where there's a large storm in your dam catchment and this generates a lot of water which then flows into the reservoir, and you have to make sure that you've got sufficient excess storage capacity to receive that water and route it through and over the spillway. So how do we do this? Well, we use two tools. The first is the catchment unit hydrograph, and this relates the unit volume of precipitation falling in a single hour to the runoff that creates from the catchment. Once we know how excess precipitation relates to the river flow, we then look to construct something called the catchment hyetograph, and this is a volume of precipitation that falls over a designated period, which we call the design storm. The process by which we do this, first of all, we find the catchment unit hydrograph, and this tells us something called the catchment response time, and then from that we're able to estimate our design storm duration. From the design storm duration, we're then able to estimate the precipitation total, and once we have the precipitation total, there are some rules about how we distribute that precipitation over the design duration to produce our catchment hyetograph. The main part of the analysis is in doing these four operations, and then once we have our catchment unit hydrograph and our catchment hyetograph, we combine the two to produce our estimate of the design storm and its impact on the runoff from the catchment. And we do that by a convolution of those two tools. So we begin with identifying the unit hydrograph for our dam catchment. Just to recap, you should all know what a unit hydrograph is, but in case you've forgotten, the unit hydrograph is the unit volume of storm runoff that's produced by a unit volume of uniform intensity excess rainfall over a unit period. And it looks something like this diagram on the right. Now, for your particular project here, and in engineering projects in general, the unit hydrograph for a catchment can be conceptualized as a simple triangle. And that's what you're going to be doing for your hydrologic design for high flows. So just a few quick assumptions to bear in mind. First of all, the excess precipitation, so that's precipitation that contributes directly to the stream flow, has constant intensity and is uniformly distributed over the time steps for which it's specified. Secondly, the unit hydrograph is based on assumptions that the system linking excess precipitation and stream flow is linear, and that means that principles of proportionality and superposition apply. The consequence of this makes the technique very powerful. It means if you get 2 consecutive hours, where let's say you get 10 millimeters of rain in the first hour and 20 millimeters of rain in the second hour, you can find out what the combined runoff from that catchment was by, for the first hour, taking the unit hydrograph and multiplying it by 10, and for the second hour taking the unit hydrograph and multiplying it by 20, and then adding the two together with a 1 hour time shift. The third assumption is that the runoff duration depends only on the effective precipitation duration, so it's independent of the intensity. So that means, whilst I just talked about scaling under point 2, we can scale the vertical axis. The horizontal axis, the time base of the unit hydrograph, stays the same, because this is a defined characteristic of the catchment. All that being said, how do we then go about estimating the design unit hydrograph? Well, we make use of a number of catchment characteristics, and we're going to use those to estimate 3 simple parameters. The first of which is the time to peak, TP, and it's the most crucial because the others are based on this. And we're going to use the main stream length in kilometers, the stream slope between 10% and 85% of the stream length, and that's measuring from downstream to upstream, that's called S1085. We're going to use a parameter called urban, which is a parameter that defines the proportion of urban area within the contributing catchment. and we're going to use SAR, which is the standard average annual rainfall. So there's a parameter TP0, which is calculated as a function of all of those catchment parameters, and then from that we calculate a parameter T, which is approximately a fifth of that, rounded to the nearest half, 1 or 2 hours. And then we combine those to calculate TP. And following that, the peak flow and the time base of the hydrograph are found directly as functions of TP. And here you should note that the QP has units of cubic meters per second per 100 square kilometers of catchment per 10 millimeters of excess precipitation. And that's how we find our dam catchment unit hydrograph. So now that we have our unit hydrograph, the next thing that we need to focus our attention on is what the precipitation total for the 1 in 10,000 year storm event would be. And that's the key design criterion for your high flow scenario. It's the 1 in 10,000 year storm event for your dam catchment. So, how do we identify the design precipitation depth and its duration for that period? Well, we're going to use something based on the UK Flood Studies report method. And in explaining this to you, I'm going to be using some key terms to describe the precipitation depth and duration. And they are listed here on the left. So first of all, we're going to be talking about an event return period, and that's going to be something like M2, M5 up to MT, and that's the precipitation value with a return period of 2, 5 up to T years. And then there's the event duration, and that can be in minutes, hours or days. And so we end up with a description of an event which is MT for D hours, or MT for D days or D minutes. And this refers to the precipitation value with a return period T years falling over duration D. Now what we need to do is to identify such values for your catchment. And the UK Flood Studies report method provides 4 key resources to help us to do this. And there are 2 maps and 2 data tables. These are all provided in Appendix F of your handbook, and they're also going to be in the next few slides. And what you need to do from these 4 resources is as follows. So first of all, there is a map that shows you the M5 2-day precipitation total. So that's the precipitation total with a return period of 5 years that falls over 2 days. And you need to find out what that is for your dam catchment. Secondly, there is a map that shows you a precipitation ratio. And this is a ratio between the precipitation total that falls in 1 hour with a return period of 5 years to the precipitation total that falls in 2 days with a return period of 5 years. And this is a key ratio. Combining these two then allows us to use Table 1 to shift the duration of those standard observations to match the duration that you require for your storm. So it then tells us the precipitation total with a 5-year return period that is spread over the D hours for your design storm. Once we've got that, we then have Table 2, and this allows us to shift that return period from 5 years to be T years. And so Table 2 lists MT to M5 as a percentage of the M5 value. So once we have used these resources, we can find for your dam catchment the 10,000 year precipitation total that falls over D hours. And that's what we're aiming to do. And that will be your design storm for a given duration and return period. So the only thing in here that we don't know so far is D, which is the duration. But that is determined by the unit hydrograph parameter Tp, and it's given by the function of Tp times 1 plus the standard average annual rainfall divided by 1000. So we can find that directly once we've found the hydrograph time-based Tp. And once we've found D, it needs to be rounded to the nearest odd integer. And the reason for that is that there will be an odd number of bars in our hyetograph. If you remember a few minutes ago, the middle bar was quite large and then there were 4 subsidiary bars. So there needs to be a central peak in that hyetograph. And so that's why we need our duration D to be the nearest odd integer. So what do these resources look like? Well, first of all, we have the map of precipitation total here on the left and the map of precipitation ratio here on the right. As I said, these are in Appendix F of the course handbook. And then we have tables 1 and 2 that I've labelled here, the first of which helps you to shift the duration of that precipitation total, and the second of which allows you to shift the return period. And so once you've applied these, you should be able to determine what the precipitation total would be and over what duration it should fall. The final stage of the exercise in determining the precipitation total is that what you will have derived is a point estimate of the total precipitation that's fallen. But what we want to do is to estimate what the precipitation will have been over your catchment area. And so in order to do that, we need to use something called an areal reduction factor, and the relationship between precipitation measured at a point and the precipitation that would have fallen over a given area for a certain duration is related in the chart here on the left, and it's tabulated in the table on the right. And this chart has been produced from the data that's in the table, so it doesn't matter which of these two resources you use. It's unlikely that you will have a duration that fits exactly on one of the lines or an area of your catchment that fits exactly on the lines, so you'll need to interpolate somehow when you figure out where in the table or on that plot your catchment sits for the duration that you've calculated and the area that you know you have. And then what you do is you apply the areal reduction factor to the precipitation total for a 10,000 year return period over D hours. And that becomes your value of P. Once we've found our value of P, we need to then be able to convert that into a value of excess precipitation. And we do that by considering the percentage runoff, and that is the proportion of the precipitation, our p-value that we've just calculated, that ultimately becomes stream flow. And this is estimated as the sum of 3 different components. For a rural catchment such as the one that you're working in, it's a function of the standard percentage runoff, and that is based on the relative proportion of different soil types in the catchment. And if you look in your handbook, it will be specified that this is the relative proportion of those different soil types, and using this equation for standard percentage runoff, you can calculate your SPR value. There's then a dynamic component of standard percentage runoff that is determined by the antecedent wetness of your catchment, and you can estimate this by a simple catchment characteristic which is plotted up here on the right, and this relates annual average rainfall for your catchment to the catchment wetness index, the CWI. And once you know that, you can calculate the correction factor for percentage runoff due to antecedent catchment wetness. And then thirdly, there's another dynamic component that increases runoff when you get above a certain precipitation threshold. And that's calculated by this simple relationship if your precipitation total is greater than 40 millimeters. So to apply this technique and estimate the percentage runoff, you need a small number of additional parameters to find in order to do the calculation of what your percentage runoff would be. So we're now ready to build our catchment hyetograph. So remember, the hyetograph is the precipitation total and its distribution over the desired storm duration. So how do we construct this? Well, we start off with our precipitation total, and here is what we will have been calculating, and we've also estimated what the duration of the storm will be. So now what we need to do is to distribute that precipitation total over that duration. So this is our starting point. So we then need to identify an appropriate storm profile for our design, and for this we're specifying that it's the 90% summer storm. And here in the plot on the right you can see that there is a summer storm profile that relates the percentage of storm duration of any individual time step to the percentage of the storm rainfall that falls during that time step. So the most intense storm hour occurs 100 divided by d% of the time. So you then need to use the summer storm profile to find the percentage of the total rainfall that falls in this hour. And when you have, you can plot that, and that's your central hyetograph bar. The 2 hours each side of the peak plus the peak constitute 3 times 100 divided by d% of the storm duration. So you then need to find the percentage of the total rainfall that falls in those 3 hours, subtract the precipitation total that you've already calculated in the peak, divide the remainder by 2 and allocate this to the hours either side of the peak. And then you successively repeat step 3 for the 2 hours either side of the hyetograph. So depending upon how many hours you've estimated your storm duration is, you'll need to continue to do that until all the precipitation has been distributed over the duration. And finally, once you have this, you need to apply the standard percentage runoff to the hyetograph bar by bar to get the effective rainfall. So now we have our storm hyetograph and our unit hydrograph. To produce our design storm runoff, we need to combine these two, and that will tell us what our design storm runoff total will be and how it's distributed over time. So each bar of our hyetograph will generate a hydrograph with the same time base, but where the peak flow is scaled to the precipitation total represented by that bar. And this is called convolution, and this is how we produce the storm hydrograph. So the magnitude of each hyetograph bar scales the magnitude of the flow ordinates of the unit hydrograph, because bar 1 and bar 5 are the same magnitude, bar 2 and bar 4 are of the same magnitude. Therefore we only need one hydrograph for each of these two, and then we have one hydrograph for the central bar. And remember that the time base of each of these individual hydrographs stays the same, but then we need to time shift them and then add them together in order to give the total storm hydrograph. And this is how we do it. So the first hour we have the hydrograph generated by the first bar, the second hour, second bar, and so on and so forth. We time shift those each by an hour, then we add them together, and we can then obtain our catchment storm hydrograph. Note that the time base of the storm hydrograph is equal to the time base of the unit hydrograph plus the duration of the storm minus 1 hour, and also that the hydrograph according to this method is the runoff for an excess precipitation total of 10 millimeters. So just be careful when you're working out how to factor the ordinates of your unit hydrograph.